Examples of free body diagrams. In this section, 4 examples of mechanisms and structures together with their correct free body diagrams will be discussed. Dimensions and magnitude are omitted for clarity. In each case, we treat the entire system as a single body so that the internal forces are not shown. The characteristics of the various types of contact force illustrated in each picture are used in the 4 examples as they apply. The first example is the truss. Consider this picture. Plain truss. In example 1, the truss is composed of structural elements which, taken all together, constitute a rigid framework, as shown here. Thus, we may remove the entire truss from its supporting to support. As we discussed in the previous articles in this chapter, each support can be replaced with its forces here. Thus, we may remove the entire from its supporting foundation and treat it as a single rigid body. In addition to applied external force P here, the free body diagram must include the reaction on the truss at A and B as shown also in the picture in these 2 points. The rocker at the B can be supported vertical force only as shown, and this force is transmitted to the structure at B. The pin connection at A is capable of supplying both a horizontal and vertical force component to the truss, as shown also here. If the total weight of the truss member is appreciable compared with P and the forces at A and B, then the weight of the members must be included on the free body diagram as external forces. In this relatively simple example, it is clear that the vertical component AY must be directed down to prevent the truss from rotating clockwise about B. This support. Also, the horizontal component AX will be the left to keep the truss from moving to the right under the influence of the horizontal component of P. We have two PX and PY. Thus, in constructing the free body diagram for this simple truss, we can easily perceive the correct sense of each the component of forces exerted on the truss by the foundation at A and can therefore represent its correct physical sense on the diagram. When the correct physical sense of a force or its component is not easily recognized by direct observation, it must be assigned arbitrarily, and the correctness of or error in the assignment is determined by the algebraic sign of its calculated value. The next example in this is a cantilever beam. Consider this picture. Cantilever beam. In this example, the cantilever beam is secured to the wall and subjected to 3 applied load as shown in the picture here. When we isolate that part of the beam to the right of the section at A, we must include the reactive force applied to the beam by the wall. The resultant of this reactive force are shown acting on the section of the beam. A vertical force V to counteract the excess of downward applied force is shown, and a tension F, these forces, vertical and horizontal, and the tension F to balance the excess of applied force to the right must also be included. Then, to prevent the beam from rotating about A, a counterclockwise couple M is also required. The weight mg of the beam must be represented through the mass center. We have also gravitational force on the beam with mg here. It is the free body diagram for cantilever beam. The next example in the free body diagram, in this example, we have represented the somewhat complex system of forces which actually act on the cut section of the beam by the equivalent force couple system, in which the force is broken down into vertical component V and its horizontal component F. The couple M is the bending moment in the beam. The free body diagram is now complete and shows the beam in equilibrium under the action of 6 forces and 1 couple. The next example is the smooth surface contact at a beam. Consider this picture for more description. In this example, the weight mg is shown acting through the center of mass of the beam whose location is assumed now. The force exerted by the center A on the beam is normal to the smooth surface of the beam in this connection point. Weighted problem. The force exerted by the corner A on the beam is normal to the smooth surface of the beam. To perceive this action more clearly, visualize an enlargement of the contact point A, which would appear somewhat rounded, and consider the force exerted by this rounded corner on the straight surface of the beam, which is assumed to be smooth. If contacting surface at the corner were not smooth, a tangential frictional component of force could exist. In addition to the applied force P and couple M, as shown here, we have two external forces, a force and a couple M and P. There is the pin connection at B, which exerts both an X and Y component of force on the beam. The positive sets of these components are assigned arbitrarily. The next example for the free body diagrams is a structure. Consider this picture for more description. In this example 4, the free Body diagram of entire isolated mechanism containing three unknown force rigid system interconnected. Entire isolated mechanism contain three unknown forces if the load mg and p are known. Any one of many internal configurations for securing the cable loading from the mass M would be possible without affecting the external response of the mechanics as a whole. And this fact is brought out by the free body diagram. This hypothetical example is used to show that the force internal to a rigid assembly of members do not influence the values of external reaction as shown. Here we have external reaction on these two supports and neglecting the internal force of the structure members and also cable. We use the free body diagram in writing the equilibrium equation, which are discussed in the next article. When these equations are solved, sum of the calculation force magnitude may be 0. This would indicate that assumed force does not exist. In the example 1 for the truss, any of the reaction AX or this example any of the reaction AX, AY or BY can be 0 for a specific value of the truss geometric and of the magnitude, direction, and sense of applied load P, A0, P load P. A zero reaction force is often difficult to identify by inspection, but can be determined by solving the equilibrium equation. Similar comments apply to calculated force magnitudes which are negative. Such a result indicates that the actual sense is the opposite of the assumed sense. The assumed positive sense of Bx and By in example 3 and By in example 4 are shown on the free body diagram. The correctness of this assumption is proved or disproved according to whether the algebraic sign of the computed force are plus or minus when the calculations are carried out in an actual problem. The isolation of the mechanical system under consideration is a crucial step in the formulation of mathematical model. The most important aspect to the correct construction of the all-important free body diagram is the clear-cut and unambiguous decision as to what is included and what is excluded. This decision becomes unambiguous only when the boundary of the free body diagram represents a complete traverse of the body or system of bodies to be isolated, starting at some arbitrary point on the boundary and returning to that same point. The system within this closed boundary is the isolated free body, and all contact force and all body forces transmitted to the system across the boundary must be accounted for. The following exercise in the chapter can be useful for more exercises. The next section is equilibrium conditions.